This is a talk on the paper Nonlinear Dynamics for the Ising model. I'm Alistair Sinclair. I'll be giving the talk, and it's joint work with Pietro Caputo from University of Rome 3. So the talk is about something called mass action dynamics, which, as we'll see, is a nonlinear analog of more familiar Markov chain linear dynamics. We'll always be working with a finite underlying set of types, which I'll call sigma. And at any time t, the state of the dynamics is described by a probability distribution over sigma. We can think of the probability distribution as giving the concentration of each type at time t. So pt of sigma will denote the concentration of type sigma at time t. Evolution of the dynamics follows by a nonlinear pairwise process. What happens at each step is that individual types, say sigma and sigma prime, come together and experience a collision and emerge as two new types, tau and tau prime. The collision itself is described by a probabilistic kernel, Q. Q gives us the probability that, given that sigma and sigma prime collide or react, that the outcome is tau and tau prime. So the overall evolution of the dynamics is written in this boxed equation here. So the distribution or the concentration of tau at time t plus 1 is given by summing up over all the collisions that produce tau. A particular collision occurs with probability proportional to the product of the concentrations of the incoming type. So pt sigma times pt sigma prime. That's known as the mass action principle. And then we sum up over all the sigma sigma prime, and we also sum up over the partner outcomes tau prime. Okay. And so of course the collision kernel Q has to be a probability distribution for each fixed sigma sigma prime. So we have this basic summation requirement. Okay, now, mass action dynamics of that kind are extremely general and can have all kinds of chaotic and other undesirable behaviors. If we want them to be well behaved, then we introduce, just as we do in the linear case, Markov chains, we introduce a reversibility property. So we say that mass action dynamics described by a kernel Q is reversible if there is a probability distribution pi that satisfies this detailed balance condition. So pi sigma prime, the incoming probability for a reaction, times the probability that the reaction gives you tau tau prime is equal to the same thing in reverse. So that's a detailed balance property for every reaction. And I've drawn a picture here which shows that each reaction can go either way in such a way as to preserve this distribution pi. So, and it's easy to check from the definition of the dynamics that if you have such a pi, if you're reversible with respect to such a pi, then this pi must be stationary for the dynamics, a fixed point. Okay, so at this point, it's maybe helpful to contrast the nonlinear mass action dynamics that I've just described, given in red here on the right of the table, with the more familiar Markov chain dynamics given on the left in green. So the basic dynamical equation, we've just seen the one for the nonlinear case. The linear case is just a familiar evolution of a Markov chain under a transition matrix, a stochastic matrix P. The reversibility condition that we've just seen has the familiar analog for Markov chains, just that each transition in the Markov chain satisfies detailed balance with respect to some distribution pi. And then we know well from basic Markov chain theory that if a Markov chain is irreducible and aperiodic, finite Markov chain is irreducible and aperiodic, then it will converge to a stationary distribution. And indeed, if it's reversible, that stationary distribution will be the one guaranteed by reversibility. For the nonlinear dynamics, the same thing holds, but is somewhat more delicate. So again, if you have a suitable irreducibility property and aperiodicity, then your game will converge to a distribution pi, which will be one of the ones with respect to which it's reversible, may in fact, in this case, depend on the initial condition P0, initial distribution P0. And I should say the irreducibility condition here is it's what you'd expect. You would want to say that that all probabilities of all types are bounded away from zero after a suitable length of time. But establishing, it doesn't seem to be a simple sufficient condition for that, as there is in the linear case. So somewhat delicate ad hoc argument required to prove irreducibility in each case. And finally, what's known about rates of convergence. Well, we know for linear for Markov chains, we know that the variation distance to stationarity is monotonically decreasing. And we also know that convergence occurs at bounded above by an exponential. So we get an exponential rate of convergence. For the nonlinear case, neither of those things is known. In fact, it's known that the variation distance is not necessarily decreasing. And we don't know whether there is a general exponential bound on rate of convergence. Okay, so that's the general picture. Now, this talk, the goal of this talk is to, sorry, my slide seems to have got stuck there. Okay, the goal of this talk is to develop general analytical tools for analyzing the rates of convergence of mass action dynamics. We have lots of tools for the Markov chains, for the linear case, but we have almost nothing for the nonlinear setting. And some applications and motivation for this I've listed here. So first, it's a natural nonlinear analog of linear dynamics that are very familiar and have proved very powerful. But it also, this type of nonlinear dynamics also arises in many fields naturally. So chemical reaction networks are described by, in a chemical reaction network, the types will be molecules, and the system evolves via reactions between pairs or groups of molecules producing new molecules. In the Boltzmann equation, which was actually where this type of dynamics was first introduced, the types are momenta of gas molecules, and collisions occur and change their momenta. Population genetics, the types are genotypes of a given species, and they react by a reproductive mechanism that exchanges genetic information between the genomes. And genetic algorithms have been proposed as a heuristic for solving optimization problems. And in this case, the set of types would be the feasible solutions to the optimization problem. So those are some motivations. I want to start with one of those motivations actually as a very simple case, which the only case essentially up to now that has been fully resolved in terms of rate of convergence and all the other desirable properties. So this is the case of population genetics, so-called Hardy-Weinberg model. So here we have the set of types are binary strings of length n, corresponding to genotypes in which there are n alleles, and each allele can take one of two values, 0 or 1. So they're binary alleles for simplicity. And the dynamics works as follows. So we take two individuals, these are just bit strings of length n, and we pick a random subset of the bits of the positions, and then we exchange the bits of the two strings at those positions. So in this example here, I've picked positions 2, 3, and 6, and we have simply exchanged the bits between them to produce these two new genotypes on the right. Okay. Now, it's known, it's fairly easy to show that this very simple system converges to a product distribution pi as t tends to infinity. And this distribution is described, it's a product distribution over individual bits along the genome. And the marginals at each bit are given by whatever they were at the beginning of the process, however it was initialized. So that's P0. So this system converges to a product distribution over individual bits with no correlations between the bits. Okay. And the same holds, you don't have to choose the random subset S uniformly. You can also choose it in any reasonable way, equitable way, and you'll get the same result. Okay, and notice that we have the marginals, marginal probability of a 0 or 1 at each position is a conserved quantity here for this dynamics. Okay, now I want to give what I think is a very nice argument, about 30 years old now, for what the rate of convergence of this dynamics. So the way to think about this is let's view a particular individual at time t, and this I've just taken the example of the string 0011. Here the strings are of length 4, and I want to draw a tree that describes how this individual was created at time t. So if you think about the way the dynamics is defined, the individual has received each of its, in this case, 4 bits from either one of its 2 parents. Either it's, so go back to the previous slide, this guy here on the output genome receives each bit from either this or this string, input string. So we can draw that process backwards, going backwards in time. And so, for example, maybe this individual received the first, third, and fourth bits from its left parent and the second bit from its right parent. And now this process continues down the tree, but we only follow the bits that actually go to the root. So here we the 0, 1, 1, maybe the first and the fourth came from the left parent, and the third came from the right parent, and so on. We keep going down, evolving this tree downwards, and we stop when all of the leaves, each leaf contains at most 1 bit. And we call that event fragmentation. Now, the point is that what I claim is that once fragmentation has occurred, we know that the distribution of the string at the root, when we pass those bits back up from the leaves to the root, will be exactly the correct product distribution pi. And that's simply because, well, we know that the marginal probabilities at the leaves are correct, because marginal probabilities are conserved in this process. And secondly, the fact that they're independent, that it's a product distribution, just comes from the fact that each bit is inherited from a distinct leaf, a distinct individual at time 0. And therefore, we will get a product distribution of the root, which is what we want. That's the stationary distribution. And so now, once you have that, it's very easy to deduce an upper bound on the rate of convergence. So just the variation distance at time t is clearly bounded above by the probability that you had not achieved fragmentation at depth t. And that, by a simple union bound, is just is bounded by n choose 2 times 2 to the minus t, just because you have to separate every one of the n choose 2 pairs of bits. And this immediately gives you a convergence time of order n log n. Okay, and this actually turns out to be tight asymptotically up to constants. Okay, now, so what this talk is really about is what can we say anything like that for the case where there are some where the stationary distribution is more interesting. I mean, this was a very simple case where the stationary distribution is a product distribution, and what if we, what if we're dealing with a more interesting example where there are correlations in the stationary distribution? And maybe the simplest type of example that exhibits correlations that are non-trivial, but bounded fairly weak, is the so-called high-temperature Ising model. And so here, I've defined it here. So we have a graph, and it doesn't need to be a lattice. It happens to be here. We have a graph, and each vertex of the graph can be assigned a spin, either +1 or -1. So the types in our system here are going to be ±1 strings of length n. And the measure that we're interested in, the probability distribution we're interested in for this model, is the familiar Gibbs measure, for Gibbs distribution for the Ising model, which is defined in this box, and it contains it's a product, actually, because of the exponential, it's a product of factors, each one a factor coming from each nearest neighbor interaction, so which is governed by parameter beta, and also from external fields that are just associated with the spins at single sites. So that's the Ising model. Now, we're going to be considering the Ising model at what we call high temperatures, which means that the interactions are weak. In particular, the beta IJs, the nearest neighbor interactions, are small. And the right definition of small is that at any given site, I, any given vertex I, the total sum of the magnitudes of the edge interactions adjacent to it is bounded by some small delta. This condition with delta equals 1 is the familiar de Bruijn condition, which it guarantees rapid mixing of the standard linear Markov chain dynamics for the Ising model. And I should also point out that if all the interactions are 0, we get exactly the Hardy-Weinberg model because there are no interactions, all the bits are all the spins are independent. And so we're just in the Hardy-Weinberg case. Okay. But here there are correlations, definitely non-trivial correlations, and we're interested in what we can say about nonlinear dynamics in this setting. Okay, so here's the nonlinear Ising model dynamics. It's very similar to the Hardy-Weinberg dynamics. So again, you take two configurations, sigma and sigma prime, and you pick a random subset. So in this case, I happen to pick this subset. And what I do is I exchange the bits between sigma and sigma prime on that subset. And so I get these two new configurations, tau and tau prime. But the important thing here is that these transition probabilities are not all uniform, because we have to preserve reversibility with respect to the Gibbs measure. And so therefore, the actual kernel that tells you whether or not to make this exchange is a rather complicated, has a somewhat complicated definition, although it arises naturally. It's forced on you by the requirement of reversibility. Okay. So that's the dynamics. So I do want to emphasize the fact that unlike the Hardy-Weinberg case, where we just make the exchanges between bits no matter what the spins are, this kernel Q now depends depends on the two incoming spin configurations, sigma and sigma prime. I also should point out that, as in the Hardy-Weinberg case, we don't need to choose the exchange set S uniformly at random. We can also choose, we can also make other choices. In particular, in this paper, we're going to consider two natural choices. One is where S is indeed uniformly chosen, and then we refer to that as the block dynamics. The second possibility is that S is just a single random vertex. So we just exchange the spin at one vertex. That's a much more local dynamics. I'll refer to that as the nonlinear version of the Glauber dynamics. Okay. So I can now state our results. We start off with a basic convergence theorem, which just shows that both the block dynamic version and the Glauber dynamic version, and indeed any reasonable version of the mass action dynamics for the Ising model, not necessarily just at low temperatures, at high temperatures, but at any temperature, will converge to the Ising-Gibbs measure as desired. Moreover, there are conserved quantities here, so the external fields that show up in the particular Ising measure that is produced are determined by the marginals on the spins in the initial probability distribution P0. Okay, and now the two main results we have are rates of convergence. So we're able to prove rates of convergence for the this high temperature nonlinear Ising dynamics, essentially the same, asymptotically the same as you get in the Hardy-Weinberg case, where there are no correlations. So for the block dynamics, where you pick random subsets S, the rate of convergence is, or the convergence time is order log n. And this requires, as I said, a high temperature condition. So we need the interaction, some of the interactions at each vertex to be bounded by sufficiently small delta. And the same similar analogous result holds for the Glauber dynamics, the local dynamics. We get there that the convergence time is order n log n under a similar condition. And that it's natural to for this to be significantly slower because this is a local dynamics. It's only affecting one spin in each step, whereas in theorem one, we're potentially involving the exchange of the entire configuration of each step. So both of these theorems are asymptotically optimal since they actually match the results for the Hardy-Weinberg case, the independent case. And I should also say there's nothing actually special about the Ising model, the fact that we only have two spins, plus and minus one. The same results hold actually for any spin system. So the Potts model, the hardcore model, even when you have multiple different spin values at each site, again, assuming an analogous high temperature condition. Okay, so those are the results. The last thing I want to do is just try to convey some sense of proof ingredients. So the detailed proofs are actually fairly involved, but I'm going to give a couple of the main ideas. So and all of the work, unlike the Hardy-Weinberg case, where it's because of the correlations that exist in these systems that we have to work quite a lot harder than for the Hardy-Weinberg case. So the first idea is something I'll call a high temperature expansion. So recall that I'm going to call gamma the probability that we actually make an exchange on of a set of spins S, given that the two incoming configurations are sigma and sigma prime. And I'm focusing here, by the way, on the block dynamics, not the single site dynamic. This is a complicated distribution because it depends strongly on the actual identity of sigma and sigma prime. However, we can write it in the following form in this box here. So we can write it as a sum over random subgraphs H of a measure on those, which is a simple Erdős-Rényi measure actually, and then the complicated piece, which is describes how you describes the distribution gamma, assuming that that you've chosen H as your subgraph. Now the subgraph H codes up correlations in a helpful way. So this subgraph H, as I said, the measure on that is they're just inhomogeneous Erdős-Rényi random graphs with edge probabilities that depend on the interactions in the Ising model. And you can see from this that the edge, if the betas are generally small, then the edge probabilities will also be small. So these will be sparse graphs. Okay. And crucially, this part of the representation is independent of sigma and sigma prime. Then the complicated part, encodes all the correlations, and but the correlations are confined to the non-trivial components of H. Okay, so H is limiting the range of the correlations that we have to worry about. And then outside H, we just pick a random subset of spins to exchange. So it's simple outside H, complicated inside H. But H itself will be small because of the high temperature condition. And then, so now, given that representation of the exchange probabilities, we can take our derivation tree that we saw before for the Hardy-Weinberg model, and we can annotate it now with more information. So at any given node K of the tree, we actually have the Erdős-Rényi graph limiting the range of correlations, and BK, which I'm using to denote the random subset of spins that we choose outside the subgraph H. And so for the Hardy-Weinberg model, you don't have the correlations, you just have these random subsets, and you just get the fragmentation process that we described before. Okay, so this is the same type of derivation tree, but it has these more complex annotations on it. And so now you again can write the distribution of the distribution of the string at the root by or the configuration at the root by a sum over these structural pieces, these news of all the annotations that occur in the tree, and then the complicated part that assigns spins to the configurations working back up the tree, given whatever annotations you made on the tree. The point I want to make is that this process, the new hat process, is it's a combination of a fragmentation process, just like we got with the Hardy-Weinberg model, plus a local growth process that's described by these Erdős-Rényi random graphs. Okay, and this part is independent of the spin, so we can analyze the evolution of the structural annotations on the tree without reference to the actual spin values. The actual spin values are all encoded up in the second part, this representation. Okay, and then the second key ingredient is, once we have this representation, we need to analyze the rate at which this fragmentation plus growth process dies out and produces singletons, from which we will construct the correct distribution of the root. And so the key point here is that because of the high temperature condition, as I said earlier, the Erdős-Rényi graphs are actually very sparse. So even though our pure fragmentation process from the Hardy-Weinberg case is perturbed by an additional competing growth component, the growth is slow enough that we can show that the whole process is dominated by a subcritical branching process and therefore does die out rapidly. And in fact, you can show that it dies out at asymptotically the same rate as in the Hardy-Weinberg case. You just get an order log n time again for convergence. And I can point out that once you've got the singletons at the leaves, the complex Ising measure that's not the product measure, but a complicated measure at the root is reconstructed through the second part of the representation. So given the individual spins on leaves, you can reassemble the correlations that you need at the root by using this process to percolate them back up to the root. Okay, my last slide is a few open questions. So it's natural to ask whether we can relax the high temperature condition to the de Bruijn condition. So instead of having a suitably small delta here, can we actually replace that delta by 1? Another natural question that's actually more general for nonlinear dynamics of this kind, is there an analog of the exponential decay, possibly with a very bad rate, but an exponential decay of variation distance with time for an arbitrary reversible mass action dynamics? Back to the Ising model, our results don't say anything about what happens at low temperatures. So if we have strong correlations, and in the linear case for Markov chains, the natural dynamics slows down exponentially at low temperatures. At least local dynamics does. But we don't know any lower bounds for the nonlinear case. It's conceivable that it might even be rapidly mixing even down at low temperatures. And finally, so as described, the mass action dynamics that I've described is not really efficiently implementable because it requires, in order to produce one individual at time t, you'd naively need 2 to the t individuals at time 0 in order to get a single sample at time t from that derivation tree. However, naturally what you would do is you would take a sufficiently large finite population and you would allow it to evolve under these pairwise interactions. So it's an open question whether a small polynomial-sized population would suffice to faithfully represent, or with small error represent, the nonlinear dynamics for a reasonably short amount of time up to the convergence time. And this question more globally is related to the so-called propagation of chaos question, introduced by Mark Katz. Okay, that's the end of my talk. Thank you for your attention.